Hey folks, just wanted to give you a quick screencast about error bars. So let's assume that you've already plotted your mean data, whether it's density or diameter, height, whatever it is that you measured for your cooking experiment. And hopefully you've plotted your columns for your 2 or 3 different conditions. Now, the thing that's a little bit awkward about this is you didn't have that many trials. And let's assume that you all didn't have many trials. So when you calculate a mean of whatever, for the left one, maybe it says 22, if you had done this a million times, like infinite numbers of trials, maybe the mean would have been a lot higher, or just a little bit higher, or even more higher than that. We don't know what the actual or the true mean would have been if you had done an infinite number of trials. So that's why we're going to calculate in these things that we're going to call error bars. And for this class, the error bars we're going to use are plus and minus 2 times what's called the standard error of the mean. And I'll explain that in just a second. But this range of +2 and -2 standard error of the mean is known as the confidence interval of 95%, which indicates that 95% of the time when you do this kind of an analysis, the true mean would have ended up within this range. So somewhere between these bars, it might be the true mean. That's the idea, at least. And I should say, take everything I say with a grain of salt, because as usual, I am lying, especially when it comes to statistical stuff. Most stat teachers would cry listening to this. So believe me when I say that I'm oversimplifying this to a great degree. So the calculations for standard error of the mean are the following. The standard error of the mean is the standard deviation of your data set divided by the root of the sample size, which for us is the number of trials you ran, the number of cakes or cookies or tempura zucchini, whatever it is. It's going to be the standard deviation of that divided by, again, the root of the number of trials. And what we're going to do, again, is do 2 times that for each error bar. And there's a separate video on how to actually build those error bars in Google Sheets. If you're wondering how to actually calculate this, please don't calculate this stuff by hand. Please, please, please do not calculate this stuff by hand. This is what a spreadsheet is built for. And here is your actual equation. So it will be 2 times, again, standard deviation, and STDEV is the formula, I get the function in most spreadsheet programs. In parentheses, put in the range of cells, and I'm assuming that your data is in cells B2 through B6, and then you can see that I've divided by the square root of, 5. So 5 to the power of 0.5. And so that's what I'm going to assume that you're going to do, and that will give you the plus or minus value to enter into the custom error bar window in Google Sheets. Now, what's the significance of this? So why should you even care about these error bars? And here I'm going to oversimplify this by actually quite a bit, but for the purposes of this class, if the 2 sets of error bars overlap between the 2 data sets, and in this example that I've drawn, they do, then we are going to generally conclude that there is no statistical significance between the 2 data sets, despite the fact that the baking soda one is higher than the cream of tartar one, right? The mean for the baking soda is higher than the mean for the cream of tartar, but we don't know if the true mean is actually higher. The error bars overlap. However, if the error bars do not overlap, then for the purposes of this class, we are going to be able to conclude that there is a significant difference between the 2 data sets. And so remember, when we are evaluating our hypothesis, it's not just that one mean is higher than the other. It is it significantly different in terms of being higher? Is it, do the error bars overlap or not? Sorry for the poor explanation. I hope that helps. Go check out the error bar building video for more information. Best of luck, folks.